Okay, so the new thing about this integral is that we're not given the region explicitly, we're just given it in terms of the limits. So notice what's going on here is that the y integral, the y value is going from y equals 0 to the square root of 9 minus x squared, and that is just the top half of the circle of radius 3. Okay, so the y integral says we just want this part, we're just integrating over this part here, but now the x integral says we just want to go from 0 to 3. That's a 3. So the region that we care about here is this quarter circle in the first quadrant. So this means theta is going to go from 0 to pi over 2. And this means r is going to go from 0 to 3. Okay, and so the integral then is going to be the following. Don't know what that was. This is the integral. These are the limits. Minus x squared minus y squared is minus r squared. So this is what we're integrating. And then remember, when you do polar coordinates, you always have the r dr d theta. And now this is a u substitution problem where u is going to be equal to minus r squared. So this means, which is a Calc 1 integral. And so writing everything in terms of u, this is 1/2 0 to pi over 2. Then u equals minus 9 to 0 e to the u du d theta. And overall, this is equal to 1/2, that's a half, times pi over 2 times 1 minus e to the minus 9th. Okay, so for this problem, we want the area that is above the xy plane, below this ellipsoid, but inside the cylinder here. So the way that we want to think about this is the projection of this shape onto the xy plane is going to be a circle of radius 3. Okay, so if we kind of, I mean, again, what's happening here is the volume has the floor is the xy plane, the ceiling is like this ellipsoid given by this equation, and the walls are the cylinder. So if we take the projection of this shape onto the xy plane, it's a circle of radius 3. So the region that we're integrating over is going to be equal to the r values in polar coordinates. The r values are going to go from 0 to 3, and the theta values are going to go from 0 all the way to 2 pi. Okay, so now this integral takes some explaining. So the r values go from 0 to 3, the theta values go from 0 to 2 pi. That's just reflecting the fact that we're integrating over a circle of radius 3, or a disk of radius 3 centered at the origin. The r dr d theta, that's the thing that always goes there when we're doing polar integrals. Now this part right here, what we've done is we've solved for z in terms of x squared and y squared, and then converted to polar coordinates. So if you solve this for z in terms of x and y, this says that z is equal to plus or minus the square root of 64 minus 4x squared minus 4y squared. We take the positive square root because it is below the ellipsoid. So that's it's in between the xy plane and the ellipsoid. So that means we need to take the positive square root. Okay, and then this right here, if you write 4x squared plus 4y squared in polar coordinates, this is just 4r squared. So what this says is 4r squared is equal to, 4r squared plus z squared is equal to 64. In other words, z is equal to the positive square root of 64 minus 4 squared, and this is exactly what we have here. This is just Calc 1 u substitution. U is equal to 64 minus 4r squared. This is du. This is what we get when we make the substitutions. Okay, so now the antiderivative of u to the 1/2 is u to the 3/2 over 3 halves. So that's 2/3 u to the 3 halves, and this gives us the following. Okay, now to go from this step to this step, this is just a Calc 1 integral, and so this is the final answer. And of course, there's different ways to simplify it if you want to. But the main thing about this problem is that to find the volume that is below one surface and above another surface, so when you want to, for example, find the volume of the surface that is above the xy plane and below some function of x and y, you just integrate that function. Just like in Calc 1, when you wanted to find the area under a curve, you integrated the function whose graph was that curve. When you want to find the area under a surface like this, if the surface is the graph of a function like it is here, you just integrate that function over the, if you want to find the volume that is under a surface, you just integrate the function whose graph is that surface over the right region.